Good morning, everyone. My name is Mirsad Hyder Shah, and I will be the host for this presentation following the autobiographies of the author of this paper that is presented in the 3C journal. The paper is titled Wireless Power Transfer via Inductive Coupling. My name is Mirsad Hyder Shah. I have obtained my bachelor's in electrical engineering from DHS Sofa University, and the co-author of this paper is Dr. Nasser Hassan Abosaq. The email addresses are mentioned below. You can feel free to uh, learn anything or discuss anything with us regarding this matter. Dr. Nasser is currently working as an assistant professor at Yanbu University College, Kingdom of Saudi Arabia. So without wasting any time, let's get started. The table of contents are as follows. Just to give you a brief introduction of what wireless power transfer is, we have included an introduction, and then we will go to literature review and learn what an inductive coupling really is, what inductive coupling circuit is, and finally we will discuss the results and the conclusion, etc. Okay, so world without wires, how does that sound to you? I mean, it's all really exciting to everyone. We all want a world without wires. Just to give you a preamble, think of your life as how it was when Wi-Fi was not around. You used to use Ethernet cables just so you can use internet. I mean, that was just so historic that you may be thinking, which world were we in, using wires and all for electricity. The future may be the same. Basically, wires hinder our technologies. Why do I say that? Because wires are growing, and as a result, a lot of pollution is also being produced, and it's not feasible for us to use wires in our technologies anymore. So we should shift something better, and that something better is wireless power transfer. In other words, Nikola Tesla described it as wiretricity, wireless electricity. And in hopes to be the first man to transfer power wirelessly, he built the Tesla Tower. The Tesla Tower was the famous tower that he built so that he can power electricity through kilometers, and he failed miserably in his plans. So, you may ask me, who came up with the idea of wireless power transfer or wiretricity? And a lot of physicists believe, or it's their opinion, that Nikola Tesla was the one to come up with the idea of wiretricity. But to my understanding, to my observation, that is not entirely correct. Nikola Tesla did build the first experimental model of wiretricity. It was actually Michael Faraday who came up with the idea of wireless transfer when he presented the law of electromagnetic induction. That was the main reason, or the main thing that inspired Tesla to build the Tesla Tower. If Faraday had not given his theory on electromagnetic induction, or specifically, we will discuss it later on, if he had not come up with the idea of transferring power wirelessly, then we would not have seen the Tesla Tower. So, wireless power transfer can be divided into two categories: NFWPT, or near field wireless power transfer; FFWPT, or far field wireless power transfer. Below is a figure attached just to let you know what wireless power transfer really is. Wireless power transfer is like you are transferring power wirelessly, as it is evident from the name. You transfer power wirelessly, and there is some sort of circuitry behind the receiver and the transmitter. Okay, so let's discuss what types of wireless power transfer do we really have. So we have the near field wireless power transfer, NFWPT, and basically it is the field of wireless, or the category of wireless power transfer, which deals with close range applications, just like you saw earlier the example of electric vehicle charging system. You have to place the coil or the charger just close to the car. If not so, your car will not get charged. Similarly, we have a lot of types of wireless power transfer or subcategories of wireless power transfer. We have the inductive power transfer, the resonant inductive power transfer, the capacitive power transfer, resonant capacitive coupling, and magnetodynamic coupling. So, what is wireless near field wireless power transfer? Near field wireless power transfer depends on the coupling of the magnetic field between the two coils. What two coils? Basically, in any wireless power transfer circuit, we have two main components. We have a receiver and we have a transmitter. The transmitter can be assumed as the primary side of a transformer, and the receiver can be assumed as the secondary side of the transformer. Think of it like this: when a transformer transfers electrical energy, it basically sends flux through the air as well, and as a result you have wireless power transfer in a transformer. So let's get on to far field wireless power transfer. That is the next thing. Far field wireless power transfer is classified as electromagnetic radiation. It means that it uses EM waves or EM rays to transfer power, and it is best suited for long range applications. Common examples may include powering a aeroplane or a drone that is in mid-air and you want to power it. How will you do it? You cannot do it with NFWPT technologies. The inductive coupling or the capacitive coupling circuits are not strong enough to just power your drone efficiently. So instead we have the type of far field wireless power transfer, and it uses radio waves and microwaves to transmit power. So let's get on to the main business, and that is, what is inductive coupling. Inductive coupling is the same as inductive power transfer that we discussed earlier, which has a receiver and a transmitter. Common applications of inductive power transfer may include wireless charging of electronic device, just because it should be placed close to the charging device, and wireless charging of electric vehicles, just as we quoted earlier, that you have to place your car close to the charging pad, and finally wireless charging of implantable devices. This was an article that I read and I discussed in my paper as well. Feel free to check it out. What we learned was you can power electric organs or implantable medical devices in human bodies without the need of cutting through the body. For example, you have a electric heart that runs on batteries. You cannot afford to cut the chest every time you have to change the batteries. So instead, what you can do is use inductive coupling in your applications. Okay, so what is inductive coupling? Inductive coupling works on the basic principle of Michael Faraday's electromagnetic law of induction, which explains how a magnetic field interacts with an electric circuit. So basically, Michael Faraday told the world that when you place a conductor in close proximity to a magnetic field or a magnetic field, it will experience a current. A current will be induced in the conductor. And similarly, what we do in an inductive coupling circuit is that we power our devices wirelessly, and we basically use the law of induction which Michael Faraday proposed in 1874. So the basic law of an inductive power transfer or inductive coupling circuit, the basic fundamental formula is phi b is equals to the line integral or the integral of magnetic flux density times the area enclosed in a given loop. So it is evident from this formula that if you want to transmit more power, or if you want to transmit more flux, you have to increase the size of the coil. Basically, the area enclosed in a given loop is the area of the coil. So if you want to transmit more power, you have to use a bigger coil. So this is a basic model of an inductive coupling circuit. What is an inductive coupling circuit? An inductive coupling circuit, as discussed earlier, transmits power wirelessly through an inductor or via an inductor. Basically, we have a transmitter and a receiver, as we discussed earlier, but the main thing here is this is just a lumped up version of the model that we are going to discuss in the next slide. So what we have here is an electric source or an AC voltage source, and we have a primary coil and a secondary coil. The primary coil transfers power to the secondary coil, and that can be used as a resistance on the right hand side or the secondary side. So basically you can power any device, whatever device it may be, through inductive coupling if the range is short. Next up is when we refer the transformer or sorry, when we refer the inductive coupling circuit to the primary side through transformer theory, we note that it looks something like this. We have a resistance and inductance, and what really depends or what really matters in any inductive coupling circuit is its efficiency. How efficiently is it transferring power from let's say the transmitter to the receiver. So as a result, we have this formula. I have discussed it extensively in my paper. Do feel free to check it out on my profile or Dr. Nasser's profile. So what we have here is the link efficiency, or the link between the two coils of the device depend majorly on the mutual coupling, and it is desirable that if you want to increase the efficiency, the link efficiency, you should increase the mutual coupling of the circuit. Well, if you want to construct an inductive coupling circuit, it's pretty simple. All you have to do is use a transmitter and a receiver. A transmitter composes of, as we discussed earlier, a voltage source, a coil, and an inductance impedance matching, basically, circuit. So the transmitter transmits power to the receiver, and from the receiver you can you can transfer the power, you can use the power however you want. If you want it DC, you can attach a bridge rectifier and then filter the ripples out, and finally you will have a DC application. Or if you want to use an AC device, you just have to filter out the ripples and use it. So these results were obtained once we put on an experimental setup, and as it is evident that with the increase in distance from 0 to 3 to 5, the efficiency in the right hand column goes down. It goes from 78 to 0.072. So it is desirable for an inductive coupling circuit to be really close, and preferably not greater than 3 centimeters. Since this was done in less funding, it achieved an efficiency of 78%, I'm sure there are many researchers who would want to increase that number to, let's say, 92 or 93. Finally, we discuss the graph. How does transmission efficiency compared with the distance? So we find out that efficiency is inversely proportional to the distance. So as we increase the distance, we find out that efficiency drops down, and it was evident from the results in the previous slide as well. Finally, what were the problems faced in making an inductive coupling? Well, one of the problems is the coil size disparity. I have written about it in my paper as well. Just to give you a quick recap, coil size disparity is the disparity in the two coil sizes. Basically, the left hand side, or sorry, the primary coil is much bigger than the secondary coil. How bigger? That is a different topic, and we worked extensively on this, and we used different methods to finally come up with the right coil size, just so we could power our load. And one more thing, the problem we faced was that there was just so much heat in the inductive coupling circuit after a long use that it was not feasible for us to continue, or the efficiency kept dropping down. So in ideal conditions, this may work perfectly fine, but in hot and humid conditions, we may experience some efficiency drop. I mean, it's just the same case like you're using your phone with your charger on. Since you are continuously feeding power, your battery tends to get damaged. So it's desired for applications of less power, inductive coupling. And finally, the one of the problems is the coil overlap loss. So basically, you have to place your coil, the primary coil, perfectly on the secondary coil, just like we saw in the first slide, on the first figure, that the electric vehicle had to come up in exactly the same place on the charging pad. If not so, power will not be transmitted efficiently. So coil overlap loss is one of the factors that users have to look at. So the conclusion is pretty simple: the wireless power transfer is the future. It holds a lot of applications, from small ranges to long ranges. I can say it for my my project or my paper, that for small range you can definitely try out inductive coupling. Inductive coupling is being done in a lot of devices. You may have seen the Samsung's wireless charging device, or your phone may be charged to wireless power. iPhone came up with that idea as well, and when we did it, an efficiency of 72% was achieved. So finally, these are the references. I want to thank all the authors of these papers, and I have mentioned them in my paper as well. Do feel free to read it, and thank you so much. Take care.